quiz I think I had email you my results. That was just off by a second.
Oh, okay. So you mean, so there's two?
Like I see 2 quiz ones.
Oh, that's weird. Okay. Yeah.
Like I have one that's on the May 3rd and one on May 5th, and then I emailed you with the one that was due May 3rd and then uploaded the one for May 5th. And they're the exact same. Yeah. Well, no, they're the exact same quiz.
Oh, then we'll just count it as one. Don't worry about it. All right. I don't know what happened there. So, all right. Yeah, I'll take care of that. Most of that stuff will shake out in the wash eventually. It's just a matter of catching up with it, I guess. So this week, I think most of you probably seen by now, we're all about eigenvalues this week, eigenvalues and eigenvectors. And so a couple of things I want to do tonight is I want to get to dealing with, you know, what are we doing when we find these guys? Number one, where are we going with these kind of things? Kind of the number two thing I want to talk about. And then I also want to show you, I want you to be comfortable doing them by hand on a 2x2, but let's be truly honest here. Once you get past the 2x2, nobody does them by hand ever. I mean, it's kind of a cute little, hey ladies, check me out. I can do the eigenvalues on this thing. Isn't that cool? Okay, weirdo. But for the rest of us, it's like, I don't know. I don't know that I need to do that much. So what we'll be doing for the 3x3s and that sort of thing, I want to teach you how to do on the calculator. But what I would really like to be able to do is to apply it a little bit as more. So that's kind of what my plan is for tonight. So just a second off camera here. This is the thing that I always forget to do, because most things you just walk in and start teaching. But these are hard to come up with so that they factor appropriately. It's very annoying if they don't factor appropriately. So let's see here. Let's do this and this. Is that going to work? That should do the trick. So if you had this 3, 2, 1, 2, if this were your A matrix, okay, we are going to find the eigenvalues and eigenvectors of this guy. Now, I'm going to write the equation down for you. Make sure I get it copied down exactly like your book does. And when you get it down, you're like, okay, well, that's neato. I did it. What did that do for me? So that's the thing I hate about when the books teach eigenvalues and eigenvectors in this setting, is because it doesn't really make any sense to you. Okay. What's the point? What am I doing with this thing? Okay, so we're gonna do a couple of applications later in the week. There's gonna be a new video, another addendum video later this week, and so that I'll add to it. I want that to be a separate thing. So the first part of the week is determinants. Obviously, if you've seen the video, you've seen that. We've talked about determinants a little bit, but that's in here as well, some of the math of determinants. But then also actually going about finding the eigenvalues and eigenvectors. From there, though, what I want to do is I want to be able to do a little application with it. So AX, that's A is a matrix times a vector X, is equal to lambda times the same vector X. Okay, and so when you have that, this guy right here is the eigenvalue. Okay, that pulls that off. And so when we look at these, we're going to be solving for this guy. You're like, well, okay, I guess. So one thing we want to do is be able to write this formula kind of like this. So we're going to have AX minus lambda X equals 0. Okay. And then we're going to take an extra step in here. We're going to do this. We're going to say AX minus lambda times I times X, where I is the same dimension as A, and of course A is always going to be a square matrix. So whether it's 2x2, 3x3, what have you. And so what we're going to do then is we're going to then do a little factoring. What do they have in common? Well, they have an X in common. Now remember, matrix multiplication is not commutative. So one has to write it like this, okay? And so what we're going to be doing is we're going to be solving, okay, for values of lambda that make this true. That's literally all we're going to go about doing. And so when we do this bit right here, what we're going to say is it's A, which is this guy, minus lambda times I, which is, oh, I shouldn't have written it that way. Well, I don't care. I'm going to write this way anyway. It doesn't matter to me. And so what you end up with is 3 minus lambda, 2, 1, 2 minus lambda. Okay, so this is A minus lambda I. Excuse me. So notice that when we're solving this, we need to set this baby, we need to set it equal to 0, 0. Yes, that's the idea. We're solving, well, back the train up a little bit. We're going to multiply it by our x vector. Remember, this is just a vector, and we need to get a vector of zeros here when we're done. We need to get, oops, I'm sorry, we need the 0 vector out of this thing when we're done. Okay. And so to do that, what we can do is we can actually solve this thing. And to do that, we can take the determinant of it. And to do it, we take the determinant of this guy, and you get 3 minus lambda times 2 minus lambda minus 2. And of course, that is set it equal to 0. And you get lambda squared minus 5 lambda plus 6 minus 2 equals 0, or lambda squared minus 5 lambda plus 4 equals 0. Now, once you're here, not surprisingly, because this is a 2 by 2, there's going to be 2 answers, and you get a quadratic out of it. So it factors, obviously. Nice. And so our eigenvalues are 1 and 4 in no particular order. Okay. Again, they are the values that make that true. Well, what does that mean exactly? Well, again, if you come back up to here, okay, when we come back up to here, we say, well, it's A times any vector x is going to equal lambda times any vector x. Okay. Prove that to me, Jay. I'd love to. So let's make a vector x, shall we? Let's just pick a vector x. Let's say our vector x is 7, 1. Seems like as good a one as any, right? And so it was our 3, 2, 1, 2. So 3, 2, 1, 2 times 7, 1. That's going to be 21 plus 2 is 23, I believe. Is that right? And then you have 7 plus 2 is 9. Nice. Very cool. Very nice. Very cool. And so you're like, okay, well, so at A times that is equal to these guys over here. Oh, okay. So what would happen then? Or in other words, when you do that, okay, go back up here. Sorry. So when we do this, we need to be able to get those same values back out, is what we're saying. So the question is, when we do this, so let me back up just here. So when we do this, that's the idea. We need to be able to make those to come out the way they want to come out. So in theory, we take these lambdas, we should be able to come out with the exact same values coming out of those as well. I think I did one of those in the video the other night, so I don't want to spend a ton of time on that. But that's the game of how and why we're going about finding these guys. That's kind of the whole key to it. Now, when it's kind of interesting, the thing that I find interesting about these is when you have something like this, and you have a quadratic, the thing that's I think the most fascinating thing about these, and we'll do some more full-on examples, but if you think about this, what are the kind of solutions you can get? Well, you could have a situation like this guy, where you have lambda minus 3, lambda plus 1. That's -1 and +3. All right, that is, you have 2 real solutions, but they're opposite signs. The previous page, we had lambda equal 1 and 4. That is 2 real solutions, same sign. And they could just as easily have been same sign but both negative. That also will play a different thing. Now you're like, wait, could they be the same? Well, sure they could. They could have lambda minus 2 and lambda minus 2. What would that give us? Well, it would give us a double root. And that obviously would have some kind of impact. And then someone might say, well, what if you had lambda squared minus, or plus 4 rather, equals 0? Oh, plus and minus 2i. Can you have imaginary eigenvalues? Yes. Are they fun? No, they're not. Could you have something like this? Oops, that's not lambda, dummy. That's lambda squared minus, I don't know, minus, plus, let's do plus, lambda plus 6 equals 0. I don't know if this one doesn't work, but I want to make sure it doesn't work the way I want it to not work. So -1 plus or minus 1 minus 4 times a times c. Oh, that nice. Here we go. So it's going to be -1 plus or minus the square root of 23i over 2. Oh, gross. Yeah, no kidding, that's gross. And so what we're going to see, plus or minus, is, again, you could have opposite signs. You could have same signs, both negative, both positive. You could have pure imaginaries. You have a double root, or you could have a plus bi situation. That is where it's a complex conjugate. Each of these characteristics is going to mean something different, algebraically speaking, behind the scenes. Okay? And so where we really see these show up and where we're going to use them the most, for those of you that have taken differential equations, you've seen this. And if you haven't taken differential equations, you will see it if you take it eventually, is a situation like this, perhaps. You might have a situation where you had, what was my original problem here? 2, 3, 2, 3, 2, 1, 2, 3, 2, 1, 2. Right, here we go. And so something like this, 3x plus 2y is equal to, well, okay, is equal to, I'm just going to say it's equal to dx dt. And x plus 2y is equal to dy dt. And the idea here is you want to solve these equations. And so what ends up happening in this situation is you want to solve these guys. And so what you'll end up doing is you'll have this, you'll set up the matrix like so. Set to 1, dummy. And you're going to find this, and you're going to find this, and it's going to be, like I said, lambda plus minus 5 lambda plus 4 equals 0. And then when you do that, of course, you're going to get the lambda equals 1 and 4. Now, what does that mean? Well, it turns out that in differential equations, and if you've not seen this yet, what we realize is that each of our x's and our y's will always be of the format something times e to the r something. And y will be of the same format, except something different. And that's something we'll tackle when we get there. Well, these r's right here are your lambdas. Okay, and what we'll find is that x will be equal to a linear combination of these guys. It'll be something like a, I'm just going to write it like this. It'll be C1. I'm going to leave a blank spot right here. And then e to the r1t plus C2. I'm going to leave a blank spot, e to the r2t. And y will be similar to it. And why did I leave that blank spot? Okay, because what's going to happen here is this. When you walk into a situation like this, you know how x is changing and you know how y is changing. Well, think back. That's all you did in Calc 1. Listen, you're here at a point and you knew what the slope was, so could you approximate it? Sure, you could. But you had to know where you started. And so what's going to happen is you're going to know an initial value for x. And you're going to know some initial value for y. Let's say it's 2. I don't know, whatever it is. Okay? But you only know 2 initial conditions. But if by my count, you're going to have 1, 2, 3, 4 unknowns. Well, there's no way you can solve this equation. Oh, yeah, you can. Because what's going to happen here, allow me to draw this in. What does that look like all of a sudden? This is a vector. A vector of what, Jay? Well, a vector of multiples in essence. In essence, the top one is going to be a multiple of what the bottom one is. Okay? So for instance, this one might be 2 and 1. In other words, this piece here is going to be twice as big as this piece here. This vector could just as easily have been 1 and 4. where the bottom one is 4 times, that constant is 4 times what this constant is, okay? And that's where eigenvalues and eigenvectors are going to come into play, okay? And so it's really disgusting and weird in linear algebra to go, okay, cool, let's find some eigenvalues and eigenvectors. And, oh, isn't that cool? You can, it'll, I guess, what's the point? Well, the point is there's a lot of very cool and important things that we're going to do later on with them. And so once you understand them a little bit, it's pretty neat. We're also going to look at a little bit of some geometry of them, some geometry that will explain why it is that these situations we looked at over here produce the things that they produce, okay? So this here is probably my favorite one. The classic is if you have a predator-prey model, if you're graphing the predators versus the prey. In other words, I'm not graphing them both versus time. We know what's going to happen. If you graph predators versus time, they're going to do this and this and this and this and this, okay? And if you graph prey versus time, there's probably going to be more prey than predators. They're not going to follow the same pattern. In fact, they might be doing something more like this. It'll be that kind of the Eli the Iceman routine. One leads the other leads the other kind of a deal, right? But this is versus time. But if you graph them versus each other, in essence, one of them is a sine curve and one of them is a cosine curve. What happens when you graph sine versus cosine? You end up with the idea of this idea that it's gonna circle or oscillate around what we call a equilibrium position, and it's called a stable center in this case, stable center. And we're going to look at that a little bit later on. We're going to look at some applications of this to differential equations. But that's a pretty classic deal where, hey, look, the predators are down. Okay, now the prey is down. Now the predator's up. Now the prey is up, and vice versa, whatever. That's a pretty big deal. Okay. Other things, you know, this could be this one here. If this had been a negative right there, well, in reality, what you're going to end up with is you're going to have e to the a plus bi times t, right? This is Euler's formula. If you FOIL that out, and if a is negative, that makes my life easier. Right? This is this. That's easy. And oops, well, no, it's not. That's that. What is this? What is e to the bt times I? What did Euler say that was? Oh, he said it was this. Wait, what does this look like when you graph it? Well, this, when you graph this guy versus on the next line down, so this might be your x, this might be your y. It'll be very similar. There's going to be slightly different because again we're going to have eigenvectors in here. It's going to be vectors here and here. I'm just going to kind of draw them the same. And what you're going to see is this: when you graph them versus each other, what happens? Well, if you graph this guy versus itself, it's going to do this. We call that dampening, okay? So it could be in the case of a predator-prey model, but it could also be in the case of if you did just this piece right here, it's very much a shock absorber on your car situation, yeah? Dampening situation like that. This one would oscillate in theory forever, but it would go to zero awfully quick because of this piece. It would just never quite get to zero. It would definitely tend to zero, never quite actually get to zero. And so, but if you graph them versus one another, what it would tend to do is it tend to spiral in on itself. That's if the A was negative. If this A was positive, it would tend to start in the middle and spiral itself out because they'd be growing over time, okay? Thank God that doesn't happen very often. That'd be weird if our populations were expanding, you know, e to the 3t or something, all right? Different ones are pretty cool. This one here, you know, we're going to look at some of these other ones later on, but there is a reason why these things exist the way they do. So we're going to look this week a little bit. I'm going to do just some different examples of, you know, what does that do for us when it comes to, what does that do to us geometrically speaking? And then I'm going to try to show you some different things in that regard. That's what the video is going to be about. Won't be any real homework in that regard to it. It's just going to be more of an application situation. It's kind of outside of what the book talks about. So, but again, to me, when I was in college and learning stuff, without an application, you'd lose me. You'd lose me. Oh, isn't that neat? You can follow this. Yeah, I guess it's not my thing. So I'm going to try to show you some examples to where it makes a little more sense. I am going to continue. I'm going to do this one here from start to finish, and it's the one we just did. Well, I think I am. Yeah, here it is. So 3x plus 2y and x plus 2y, 3x plus 2y. Okay, and x, I'm just going to say x of 0 is 7 and y of 0 is 2. That's just an initial condition. And so again, we believe that our solutions will be of this format, and this is something that you have to take on face value because you've not been in DiffEq class. So at this point, you're just going to have to believe me. You're like, Jay, this looks stupid. It does. So I'm going to show you how I will write it differently if you don't want it in a second. Oops, this should be R1 down here. Sorry. And so what a normally person would do is write it like this. X, which is this vector right here, is equal to C1 times this vector, which would be V, and we'll call it V1, e to the R1t plus C2, this is V2, e to the R2t. And so we already said, hey, our characteristic equation came out to be this guy, and so lambda minus 4, lambda minus 1. So our lambdas were 1 and 4. All right, cool. Which means I can fill this in like so. Don't know what that is yet. We'll figure that out in a minute. E to the t plus C2 e to the 4t. Okay. Now the question is, how do we find this guy? Well, to find this guy, this is the one that's associated with the number 1. So what we're going to do is come and make our a minus I lambda. Okay, and we're going to stick this in there. And so when we do this, we're going to put lambda equals 1. So we're going to get 2, 2, 1, 1. We're going to multiply that by something. Your book doesn't use A and B. I was always taught to use A and B, and it's always stuck in my head. But you can call it whatever you want. When you distribute this out, you're going to get 2A plus 2B equals 0. And you're going to get A plus B is equal to 0. So pick me a number, not 0, 0, that makes this work. Well, somebody would say, let's let A equal 1. Well, if A is 1, what does that make B? B negative 1. Cool. In other words, they're the same equivalent ratio, opposite signs. Somebody else might very well say, I'm going to do 7 and negative 7. Cool. Weird, but you do you, friend. So what we just found was these guys will have the same equivalent amount, opposite signs. If someone here had used 7 and 7, then you and I will get the same answer when we're done. We'll have different C1s, but we'll have the same coefficients when it's all said and done. Because remember, we're going to take C1 times 7 is our coefficient. And we're going to take C1 times negative 7 as our other coefficient. So your C1 will be smaller than my C1, 7 times smaller. And when it's all said and done, we will get the exact same answer. But I personally am going to use 1 and negative 1 because it's easier. I don't like to think that much. Now, if I plug 4 in there, I'm going to get negative 1 and 2. And then I'm going to get 1 and negative 2. No way. A and B, 0, 0. And again, that's negative A plus 2B equals 0. Well, I feel like 2b is equal to a. That's right. Well, could a equal 1? A could very well equal 1, but that would mean b would equal a half. So personal preference, if you're me, if I'm you, I'm going to let b be the 1. But you do you. And if b is 1, then that means a is equal to 2. Cool. So my vector would be 2, 1. Now someone else might say, well, I let a equal 1. Okay, that's nice. So if you let a equal 1, that means b is equal to a half. But you'll notice that it's still a 1 to 1/2, but it's still a 2 to 1 relationship. The top one is still twice as big as the bottom one. If I ever got to this situation here, the very first thing I would do is times by 2. And I would get something that didn't have a fraction in it, probably if it's me. I like fractions by more than the next guy, but there's no need to work with fractions if you don't have to. And so this thing right here is the vector format of my answer, but I could also break it back out. So C1 times 1 is C1 plus 2C2, e to the 4t rather, sorry about that. And y equals negative C1 e to the t plus C2 e to the 4t. You're like, that's cool. What does that tell me? Well, remember, x of 0, we said was 7. Y of 0, let's say, was 2. If you plug those in, e to the 0s are just 1s, and so that transforms into C1 plus 2 C2 is 7. And you get negative C1 plus C2 is equal to 2. So if you solve that, this would be add. Oh my goodness, it's like I know what I'm doing tonight. Weird. So C2 would be 3. And I guess that makes C1 equal to 1. So my final answer would be x equals e to the t. And 2 times 3 is 6. And you'd get negative 1. And you'd get plus 3 e to the 4t. And that would be the answer that you would have solved for. And we used eigenvalues and eigenvectors to get there. Okay. Now, again, there's a reason for our madness. There's a point in which we had to do this. Those vectors right there are huge. Again, we only had 2 unknowns, but in reality, we had 4 unknowns. So when you stop and think that these guys here are the same, you'll notice that they're the same. They're just the same. There's a ratio there. They're opposite signs. They're 1-to-1 ratio, but opposite signs. This one here is a 2-to-1 relationship. So whatever C1 was, it's, the top one's double it, and the bottom one's just by itself. Okay. So a couple things to think about on that. I'm gonna stop sharing and share something different with that. Oh, brother. I guess this is the one I want. Desmos today. Sounds fun. Nice. So what I want to do is I want to graph these 2 equations. And so my equations were, what were they? E to the t, we're just going to use e to the x, plus 6, e to the 4x. Yeah, that's going up like a bat out of heck right there, and it's not coming back. So if this was your population of bacteria, you've got a problem. That's terrible. And so what's kind of nice about these things is in real life, frequently things tend to 0 over time. So frequently, it's not going to be e to the x and e to the 4x. It'll be more like e to the negative x and e to the negative 4x. Just typically, because that's just what happens in nature. Typically, things don't blow out of proportion to the point where you can never stop them. E to the 4x. Cool. And there they are. They're being graphed one versus another, I guess. You look at that. Isn't that exciting? At 0, it's equal to 2. Yep. At 0, it's equal to 7. Yay. That's cool. So that's all fine and dandy, I guess. What would happen, however, now remember, these are right now, this is x equals and y equals, right? And my x's that I see right here are technically functions of time. And so I could graph this versus one another, and I'll talk about that later in the video, because right now we're graphing each of them in essence versus time. Doesn't take much time for them to blow up to infinity, okay? What I'm going to do this week is I'm going to graph the red function versus the blue function. And so, you know, whatever the red one is, maybe that's, I don't know, predators. I hope not. And the blue is prey. Again, I hope not. And then I'll graph them versus one another. X for predators will be on the x-axis, and predators will be on the prey will be on the y-axis, and we'll graph them and kind of see where they're going with that, so that you can kind of see how they play against one another. Something else that I want to see on that is this. What would happen if you took the derivative? Oops, come back. Stop it. Oh, I stopped sharing. I got to reshare. Sorry. What would happen if you took the derivative of x right here? Well, the derivative of x with respect to t is e to the t. Is that right? And then the derivative of this would be what? It'd be plus 24 e to the 4t. Is that right? And then that's interesting. So wait a minute. Over here, it said that dx was equal to 3 times x plus 2 times y. Well, what would 3 times x be? 3 times x would be 3 e to the t plus 18 e to the 4t, and then plus 2, so times e to the negative 2t, or e to the t, whatever, plus 3 e to the 4t. And so if you do that, lo and behold, you will get 3 e to the t minus 2 e to the t plus 18 plus 6 is e to the t plus 24 e to the 4t. Okay, and so what you're doing when you do that situation, what you're saying is you've looked at it in terms of you've solved the systems of equations. Number one, yes. You've said that the derivative of x with respect to t is a linear combination of the x and the y function, okay? And in order to get there, we had to use the eigenvalues and eigenvectors. So we're going to be doing that this week. It's not terrible. It's not awful. It's almost fun. And so we're going to be doing that. I'm going to be using the computer to do that. And so I'm going to break out my TI right now, and I'm going to share that as well. I'm going to do one out of the book that I know has a decent answer. What I don't want to do is spend 2 hours mucking one up that doesn't have nice answers, and then people will be all upset because, well, Jay, thanks for wasting our time. I appreciate that, pal. I just find that annoying. This one here, I believe, has good answers. 3, 1, negative 1, 0, 1, 2, 4, 2, 0. Okay. Not that difficult, I guess. So in other words, you could do this. And then you could do expansion by minors. Oh boy.
You can't see what you're writing.
Why not? This is terrible. I'm sorry. Somewhere I pushed the wrong button, apparently. Sorry about that. Oh, here I am. So I could do expansion by minors is what I was getting at. If I had that for an A, I could do this. I have better things to do with my time, so I'm not going to do this. But this is what could happen if you wanted to. Or if you're on a deserted island or something. I could see the professor on Gilligan's Island playing this game. All right. Notice that when you do this, this times this is going to give you a quadratic, times this guy here is going to give you a cubic. You're going to get a cubic function out of this. A cubic function means I'm going to have 3 answers when it's all said and done. However, what I want to do I want to bring up my calculator here and share that with you. What I'm going to do is enter this matrix in my calculator. And it's so 3, 1, -1, semicolon 0, 1, 2, semicolon 0, bracket, hit enter. I just like to enter them ahead of time. And then it's second math, that's number 5 button. Number 4 is matrix. And then if you scroll down a ways, you will find eigenvalues, which is number 9. So you want the eigenvalues of this matrix. And they are that. Now, I'm glad I picked this one. That is 1, 3, and then that is the calculator's way of saying 0. Because the calculator finds these by way of numeric solutions. And so it got close enough to 0, said screw it, but it didn't round it off to 0, it just said E minus 13. So our eigenvalues here are 1, 3, and 0. Come on, move, move, move. I'll reshare I'll reshare now. Okay, so my eigenvalues are 1, 3, and 0. Now, the cool way to find the eigenvectors is simply to take your calculator and just come back to the start of this guy, get rid of the L, just delete it out, and then alpha C, and it will give you the eigenvectors. Okay, and there they are. Now, a lot of people get all weirded out by this. I mentioned this in the video. Okay, this is just a ratio. That's all it is. It's a weird ratio, but pay attention to it. 0.447, like it feels like that's like half of 0.894. That's because it is. And if you wanted to, you could prove that to yourself. Negative 0.89442719 divided by 0.447 2135955. Ta-da! -2. And so they go in order. The calculator gave us the eigenvalues of 1, then 3, then 0. So the first vector it spits out is the one that goes with the 1. And so it is 1, -2, and then 0. Where is my calculator? There's my calculator. Okay. On the second line over, you're like, boy, I don't know, Jay. I don't know what goes into there. Well, I typically start off with the big one, so 0.69631062383 divided by 0.1740776555955. Oh, look at that, it's 4. Dude, that's awesome. So in this case, it's going to be, notice that they are all, where did it go? Oh, yeah, I'm on it. Sorry, there you go. Notice that they're all negatives, okay? Now, why would they do that? Why would they make it all negative? I don't know. It's a good question. So I'm going to make them all positives. So we're going to have, when I look at this thing right here, we're going to have, we got, that's 1 to 4 to 4 relationship. And then the next one, I think that's pretty clear. It's 1 to -2 to 1 relationship. Okay. Those are our eigenvectors. Okay. So in the case of what we just did in the case of the one we just did, that would help us to solve our systems of equations. In fact, our systems of equations would start off with a dx dt and a dy dt and a dz dt in this case, because it's a three systems sort of deal. And what you'd end up with is you'd end up with a big fat X, which would be X, Y, and Z, would be C1 times 1, -2, 0, e to the t, was it e to the, yeah, e to the positive t. Oh, you can't see this, damn it. There you go. And then you'd have plus C2, 1, 4, 4, e to the 3t, because that was our next guy, yes? And then you'd have plus C3, 1, negative 2, 1, e to the 0t, which is just 1. So these last guys would just be constants. That's the real point of what we're doing, okay? That's the whole point of why we want to find eigenvalues and eigenvectors, okay? So we're going to be looking at, as I say, some geometry that goes with this week. You're going to be looking at a little bit of that. You'll be looking at doing some applications with that. So if you have looked at a little bit on in section 1, 4.1, you'll notice I skipped over a little bit of those weird graphs right there. We're going to look a little bit about that when we get into some of this stuff going on. It will make a little more sense maybe to you, maybe not. Some people find it more annoying, but if you like it, cool. If you don't, that's cool too. It makes no real difference to me whether you like it or you don't like it. You got to get there. I think I was going to mention too, your book. I think I mentioned this in my video this week. The way I like to do these guys when I do them, if I was going to do these solving, I like to do it like this. When I find my eigenvalues, vectors by hand. Your book uses, unsurprisingly, an augmented matrix to pull it off. Okay, and so you're like, oh, R1 minus 2R2. Oh, that's cool. And what do you end up with? Well, you end up with 2, 2, 0, 0, 0, 0. First of all, what does that say to you? Well, it says there's an infinite number of solutions. Yeah, that's right. And then you're like, well, I'm going to divide this top one by 2. Okay, cool. And then you're like, well, it could be what? Well, they have to be opposites of one another. Oh, okay, cool. And then you just stick in values to make the job done. I like that method in some respects, just from the standpoint of it, like it helps fill in the bit that it's completely arbitrary how you go about doing it. You've chosen some values, yay, and then you can make it work with anything. Okay, there's an infinite number of values, very much like when you're mixing chemicals. That one we did with those couple, that's kind of a hokey problem, like, oh, you solve it. Hey, look at that. It just has to balance the equation, but you could have a lot more or a lot less. So, there it is. That's the idea of them as we go along. So, let's come back to this one here. We'll do one more, I think, and then I want to show you this deal, and then we'll see what happens. 2 minus, so I'll do this one, we'll do this one 2 ways. 3 minus lambda, 4 minus lambda. I can't do this in my head, so I have to do it on paper. It's 12. Let's do 5 and 4. That's cool. So that'd be minus 20. So it'd be lambda squared minus 7 lambda minus 8 is 0. So lambda minus 8, lambda plus 1. Nice. And so you get lambda is negative 1 and positive 8. So those are my eigenvalues. Okay. If you're going to try to find your eigenvectors, and again, I'll do them both ways. I'll do the calculator and this way. I'm going to plug in the negative 1. 3 minus a minus 1 is 4, and you get 5. Remember, has to equal 0. And then you get 4, and then 4 minus 1 is also 5, equals 0. You can just do R1 minus R2, and you would end up with this. I think a normal person goes, hey, 4A plus 5B equals 0. That means 4A is negative 5B. I think a smart / normal person goes, listen, I'm going to make A equal to 5 and B equal to negative 4. Awesome. But a weirdo, but again, who am I to judge, might divide by 4. And then that person would get 1, they would get 5/4, 0, 0, 0, 0, whatever. And then you would have A is equal to -5/4 of B. But then a smart person would go, listen, I want to choose my B to be a multiple of 4. I know, let's choose B equal -4. -4 times -5/4, shut up, it's 5, okay? No matter how you get here, you're gonna get the exact same thing, 5, -4. What if someone had chosen 10 and -8? It's the same thing, dude, it's the same thing. Now, plug in your 8s, 3 minus 8 is -5, 4, and then -4. It's quite clear that if you take 4 times the top guy, and then you add 5 times the bottom dude, they should go away, right? I believe so. And so you will get -5, 5, 0, 0, 0. And then, of course, divide by 5, just make my life easier, I guess. So, in other words, -A plus B is 0. That just means that B and A are the same. Well, if B and A are the same, the easiest ones to choose them to be are 1 and 1. Okay. So this is where that first formula is that I wrote down that I kind of biffed up earlier. So when I wrote this earlier, when I wrote A times this x value equals lambda times some x value, it is quite clear that this vector is a special vector. Well, what vector is it? It's the eigenvector. And so our A is here was 3, 5, 4, 4. Okay. So times our eigenvector, so 5, -4. Why did I choose this one? Well, I'm going to choose this guy because I'm also going to use this guy right here. And let's see what we get. That's 15 minus 20 is -5. Is that right? And then that's on the top. And then on the bottom, you're going to get 20 minus 16 is 4. Now, no way. -1. No, it's the same. And it's quite clear that it will not work for just any vector. There's not just any random vector that you can pull that off for. Okay. For instance, I don't know, let's say you want, like I'm not sure if that's right, Jay. Well, let's try with 1 and 1. That's 3 plus 5 is 8. Yeah, that's not equal to -1. So you can clearly see it isn't going to work. They have a special relationship. The same thing can be said for the other one. So 3, 5, 4, 4 times our other vector. But remember, isn't that the one I just used? However, what was I using? I was using the other eigenvalue. I was using the wrong eigenvalue for that one. So had I done this, because this eigenvalue must go with its eigenvector, they must go hand in hand. So it's 3 plus 5 is 8. 4 plus 4 is 8. Nice. 8 and 8. What? Look at that. Oh, it's not divided by, you idiot. But there it is. Okay. That is a special deal. It only works for the eigenvector and the eigenvalue. Okay. We will be, again, doing this to find them. Doing them to do something interesting with them. That's what's cool about this. So again, the geometry we use this week will foreshadow some stuff that we'll see when we get into systems of equations and differential equations. If you take that with me, I spend quite a bit of time using eigenvalues and eigenvectors. I think they're probably the best way to solve systems primarily. I think they're the easiest way to go. Although, not gonna lie, when you go to find eigenvectors rather, with complex eigenvalues, they're gross. They're just gross. And so just be aware of that. That's life. Life is messy sometimes. Okay. So in the homework this week, you're going to be doing section 1. It's going to be finding some eigenvalues, or given an eigenvalue, find an eigenvector to go with it. Very straightforward kind of thing. Section 2, determinants. Okay, so we already know how to do determinants. I kind of teach that ahead of time because to me, that's where it belongs. Okay, so that's a nice little review deal. There's some things about determinants that I didn't go over a ton, like what happens if you multiply by a constant to your vector first and then take the determinant. You know, I run through that this week in the video. And then in section 3, you start from scratch. Hey, we're going to find eigenvalues and take the eigenvalues and find eigenvectors. Okay, so again, in the calculator, just right here. Okay, some things to think about. And again, I mentioned this, I think, a little bit in the video, but I want to make sure I'm clear on it. Bracket starts your matrix. Semicolon defines the end of the row. There's another way to do that, but it involves having a double bracket out front and then a single bracket, then open another bracket. It's a little more of a pain in the butt. I stumbled into this a few years ago. Someone mentioned it to me offhandedly. I think they read the manual. I never read the manual. I'm like, oh, how about that? There you go. There's our 2x2 matrix. So second 5 is math, and then number 4 is matrix. Number 9 is eigenvalues, and like so. On the next test, you'll have to be able to do them by hand as well. For a 2x2, it will not make you do more than a 2x2 by hand. It's not going to do it. You'll be using the calculators to deal with those sorts of things. Again, they're there. Pay attention to which order they gave them to you. Okay, that's a big deal because the calculator will give you the vectors in the same order. So just alpha C. And not only do you have to do alpha C, you could do it that way. You could also go back in, and you can it's second math 4, and then 0 it comes after 9, I think. But whatever, it's the next one down the list is also eigenvectors. I find it easier to change that. And so 0.707 and 0.707. What is that? Well, it's 1 and 1. They're the same. They're the same top and bottom. Okay. This next one over here, like, I don't really get those, Jay. Those are weird, different, and strange. You're right. They are weird and different and strange. But if you do this, negative 7.7, sorry, 808,688. 09443 divided by 0.624695047,554, and you get 1 1/4. 1 1/4 is really 5/4. You with me? So it's that same relationship. It's just maybe it's not as obvious for you. So go ahead and divide them out. It gets you in the right frame of mind. If you prefer, and you're more than welcome to do this, you're also welcome to do them the opposite direction. You'll see it's point. Oops. Well, I swear I do teach math, friends. Maybe if I use parentheses, it'll work. How about that? Hey, look at that. It's 0.8. 0.8 obviously is 4/5. So 1 is 4/5 of the other one. Okay. I don't really understand why it doesn't round that to 0.8, but round the other one to 1 1/4, but whatever, I just work here. Just be aware of those going in. That's kind of a big deal. The reason it does this, and it was pointed out to me a couple years ago, we were talking about some stuff, and somebody says to me, like, how did they put that there? Like, you realize all they're doing, Jay, is they're just finding that they're just, those are unit vectors is all they are. They're unit vectors. I'm like, oh yeah, now how about that? And so when you come down here, if you're not sure of that, you know, think about this. If it was 1 1/4, if your vector was 1 1/4, comma 1, right? What is the length of that vector? I don't know. It's a good question. Well, it'll be 1.25 squared plus 1 squared is that thing. Okay. But then if you did this, what if you took 1.25 divided by this guy? You would get that. And then what if you took 1 divided by this guy? Well, you'd get this. And there they are. Like, I don't recognize those guys, Jay. Well, so it isn't always is, oh, wait, you know what I forget to do? I forgot to square root. That's my problem. Let's try that again. 0.5. There we go. I bet it works now, Jay. So if I do 1.25 divided by this, which is the actual length of the vector, I'll get 0.78. There you go, big moron. And then 1 divided by that, and you should get 0.62. So that's all they've done, is they've made a unit vector. So the other vector was 1 and 1. They were 1 to 1. So it'd be 1 plus 1 is 2. The square root of 2 is square root of 2, of course, 1.41. And so if you do 1 divided by that guy, you will get 0.707. Okay, so that's where they're coming from. They've created your unit vectors. Whatever. It doesn't do really any good to sit and fight about it. It's just how it is. So then what you have to do is be able to work to a situation where you can get your hands on it. Okay, come up with the ratio. That's what it's all about. The ratio is 100% what it's all about. Okay. So probably by Wednesday, I'll have the new quiz up and the new video up. There's one thing I was working on. I had to finish working on some more of this geometry piece of it. Just want to hopefully get a little bit more of I hope a little more intuition for you. I think that it makes a ton more sense when you're in differential equations, why it works the way it works based on your graphing the systems of equations together. That to me just makes 100% sense. From a strictly algebra geometry standpoint, it's a little harder to sell, but I'm going to attempt to do my best to make that happen this week. Okay. Yeah. Questions at all? I think for the most part, once you jump in, you'll find them to be fairly straightforward. It feels like you're just, and it does. At this point, it feels like you are doing, well, I found them. What am I going to do with them? And so what I hope by the time that you watch the other video, and then of course, I can't really do a ton with them until we really get on down the line of ways. I hope that once you see what they are useful for, they make a little more sense. But just playing the game is not very hard to do. But this is not a class to punish you. So again, no 3x3s, no 4x4s. I'm not going to do that to you. It's the 21st century. A 2x2, yeah, I'll make you do a 2x2 on the test by hand. Show all your work, all that stuff. But that's it.
We have a project. The term when should we work on that, or when does that start and all that?
Well, I think next week we'll put it out. Don't stress about it. It's not a very difficult project. It won't take much longer, but what you need to have eigenvalues. You need to know what we're doing this week and a little bit of next week before you can really start working on it. So,
okay.
But for the most part, my projects, I figure you spend about probably 3 total hours, maybe 4. I don't know. Greg, what do you think? Have I ever worked you overly hard on these projects? Greg's probably eating lunch. He's probably not even paying attention. Greg, are you there? Hey, he is there.
Okay. I just had to run across my room real quick to my mic. The last one for vector calc maybe like 8 or 10 hours.
Good Lord, this won't be that hard. Really?
But for stats, it was like 3.
Yeah, there you go. It'd be probably 3 or 4.
The bike was the hardest part, the vector calc.
Which part?
The data.
Oh, the data. Yeah. Yep, that's true. That took a while. All right. So yeah, I don't know. I try not to kill people off on it, and that's true. The vector calc one, you did the one with the latitude and longitude, huh?
Yeah.
Yeah, that's
pretty tough. All those exact coordinates.
Yeah. All right. So yeah, 3-4 hours I would say tops, but I don't know. Some people like to drag projects out all the term. I figure that's just too much work, and I really have to go nuts grading the thing. It's already a lot of work. It is to grade stuff. So anyway, any other questions?
No, I was just curious about that.
All righty. Well, thanks for asking. All right, everybody. Well, give me an email if you have any questions. I'll be online at noon tomorrow for our my regular office hours. I'll hang out for about an hour. My boss today, she moved next week's meeting to noon. So I'm really debating. I think I'm just gonna tell her, sorry, I got a previous engagement. I'll come and hang out by myself online. I want to listen to her. That'll be fun. Anyway, it's funny. It took the staff 10 or 15 minutes to decide what we're gonna do next week because we don't have school Monday. I'm like, why don't you just tell us what day you're gonna have the meeting? You're still the boss, but no. So apparently it's Tuesday at noon. So I said, well, whatever. So anywho, all right. Well, let me know if you have any questions. Give me an email, and I'll try to get you the those sheets in the next couple of days of what you missed on the test and stuff. So
Is the homework going to be due next Monday then?
will the homework be due next week? Yes, there should be another batch due next week, I believe.
Yep.
Yep. Thanks for keeping me straight on that. All right. Well, have a nice evening, y'all.